Hello and welcome. We are live for another Quarkus Club live call, if you like. We need to figure out a fancy name for this, right? Quarkus, Quarkus Club call. Today we have a special guest. I want to give you a kind of a fun fact here. Holly was really requested, and thanks for Georgia for doing the bridge, right? The communication, and hopefully she's here, and we have a really nice. She's going to talk about a really nice content, Quarkus efficiency. I kind of really keen in virtual threads, so fingers crossed she's going to say React is going to die in virtual threads the future. Who knows? If you are watching this, please go there and write from where you're from. Make sure that you bring your questions, right? She's going to try to answer everything. If you're not aware about Quarkus Club, is a Discord group open for everybody. Despite the name, we talk about Java, we talk about Kotlin, we talk about other frameworks. We're not here to sell Quarkus and say that's the better solution. Sometimes we really like to say bad things as well. So open for everybody. You can go ahead and say bad things about Quarkus. No one cares. If you're Spring fan, if you don't like or like, doesn't matter for us, right? So I will bring our fancy guest today for here. Hello, Holly. How's it going?
Hello.
Nice to have you. As I said, like lots of requests for you here. So, behalf of the community, thanks so much for your time. Thanks so much for you being here, and thanks George for doing this bridge communication. Right. I will add your screen here, and I will just remove myself. Feel free to. So, guys, if you're watching this live, please feel free to send questions and write where you're from. We want to hear people from worldwide, right? Thank you.
Oh, thank you very much for inviting me. I'm delighted to be here virtually. Although I have to sort of start with two disappointments actually. The first is that I have nothing in my talk about virtual threads or about reactive. Although I will say that reactive can be very efficient for certain use cases, but those use cases tend to involve a huge amount of scale. And for the rest of us who aren't operating with that kind of scale, we can just not use reactive, which makes me happy because I'm lazy. And the other sort of disappointment is that although this is a Java group, I'm actually going to start by talking about Rust. And the reason I'm going to start by talking about Rust is partly because I always feel a little bit guilty that because I'm lazy, I've never taken the time to learn Rust. But because of that, I'm going to start by saying bad things about Rust. Now, when we think about Rust, of course, the first thing that most of us think about is the efficiency of the language. It's very fast. It's very efficient. But that comes with a downside, which is if you read the internet about Rust, what you will see is lots of stuff about how Rust is too hard to learn, or, Rust is too difficult to be widely adopted. And what makes me laugh is that even if you find pages from people, who really like Rust, they still write articles with titles like "Why Rust is Worth the Struggle." And then they say, oh, you might approach Rust with trepidation because it's got this notoriously difficult learning curve. And so, if the fans of Rust are saying that, it's pretty hard. And a lot of people, in fact, say that Rust is the hardest programming language that they've ever learned. And one of the things that makes Rust efficient, sort of, is that it doesn't have garbage collection, which is also only a sort of, because it does have reference counting, which is a form of garbage collection, but we won't worry about that. So what happens if you give Rust garbage collection? Well, if you look at the efficiency of the people who are using Rust, if you overlay garbage collection on Rust, there's something kind of interesting, because it seems like you've just sort of violated one of the principles of the language. But people who are programming with it are more likely to complete a task, and they required only a third as much time. So changing the language all of a sudden made it much more efficient for people. And so then you kind of say, well, actually, I always thought of Rust as efficient, but Rust can be really slow to learn and then really slow to develop in, even once you've learned it. So maybe actually Rust isn't all that efficient. And I think we have this sort of trade-off here with Rust where, I mean, it's a trade-off that you always get actually, where you've got kind of a trade-off between machine efficiency and human efficiency. And with Rust, they've gone all in on the machine efficiency, which is kind of good, but means it's definitely not for everyone. And so then the question is, well, can we do better? And this is where we now get back to Quarkus, because I really like to think of Quarkus as a Java framework that gets you going faster. And you probably, if you've seen anything about Quarkus, you've probably seen some of these metrics, because Quarkus applications start incredibly fast. And as well as starting fast, they actually require very little memory. So you can have a really high deployment density, which is useful if you're paying for your cloud hardware, or if you're using virtualization and trying to cram as many applications in as possible. And Quarkus can run in two modes. It can run as a natively compiled binary using GraalVM, or it can run as an ordinary Java application. And these graphs here are with Quarkus as a GraalVM application. But even if you run it as a native application, you still get this really quite good deployment density. And here I'm comparing it to other cloud-native Java frameworks that many people use. But the interesting thing about this is still really impressive even when you broaden the comparison and look at other languages. So when you compare it even to something like Node.js or something like Go, Quarkus on GraalVM is, really in that competition, and it's beating Node.js. It's got this great deployment density. And if you've just sort of read an introduction to Quarkus, this is probably where the introduction stops. But one of the things that I really wish we would talk about more with Quarkus is throughput. So a while ago, we did we had sort of an independent company do some benchmarking, and we found that the baseline was that the other cloud native stack got about 3,000 requests per second. And if you ran Quarkus as a native application, the throughput was similar, but it was lower. And that's kind of exactly what you expect, right? So Quarkus on native, it's got this tiny footprint, it's got this high startup speed, and you say, okay, well, I'm making a trade-off of throughput against footprint. And that's sort of a trade-off that we expect to see, and we do see with native compilation, is you trade off your startup time against your throughput. And with native compilation, they've gone on the side of, okay, well, let's have better footprint, let's have better startup time. Now that I should say that trade-off is getting better. So native, they've done really great things with GraalVM. The throughput is getting better and better. But this isn't just a GraalVM thing. This is a classic trade-off that if you look up computer science trade-offs, this will be one of the first trade-offs you see. But it gets kind of more complicated if you look at Quarkus on JVM, because instead of having this trade-off of throughput against footprint, we have better footprint, but we also have better throughput. That's kind of unexpected. Like normally, we're so used to in computer science having these trade-offs, and here we don't have the trade-off. So instead of having footprint on one side and throughput on the other side, we've got them both on the same side, and they're better, which is kind of cool. So this is really, sorry, you can't read that because for reasons, but this is really a double win, which is something that I'll come back to, because I think if you can get that double win, it's so good. Now you may be looking at this and saying, well, not totally sure I believe you, Holly, especially because I've seen seesaws and I know that seesaws do not fold in half. It turns out you can actually get seesaws that fold in half. So if you learn nothing else, now you know you can get folding seesaws. So how does that work? How did we beat this trade-off? What's the secret? Well, of course, there isn't just one secret. So what are the secrets? And I'll go through some of them now. And I think with a lot of the things that the Quarkus team did to kind of beat this trade-off, it was about challenging assumptions and saying we've always known this to be true. We've always done it this way. What if we don't? And I think this is really important because I don't know if you've heard the expression that when you assume, you make an ass of you and me. And I have helpfully illustrated an ass here for you. That is an African wild ass. And I think that's only half true, because the world is complex. In order to make any kind of sense of it, you have to have assumptions. You can't just keep re-challenging assumptions all the time or you won't get anywhere. But you also do sometimes have to say, okay, now's the time. I'm going to challenge the assumptions. I'm going to find those assumptions that are outdated, those assumptions that don't make sense anymore, and I'm going to revisit them. So one of the first assumptions that the Quarkus team challenged, which I find really interesting, is they said we shouldn't be dynamic. And like that, I find quite counterintuitive, because normally when we think about efficiency, we tend to think of efficiency as something where, in order to be efficient, you have to be on demand. You don't want to do work unless you have to. You just, want to, only do the work if you need to do it. And that, lazy execution and all of that. And there is a place for that, but it's not always the right thing to do. And so with Java and how Java has been running since forever, it was optimized for a pretty specific kind of usage, which was you would start your Java application and you didn't like your ops team and you didn't talk to your ops team. So you wanted to make sure that once you'd started it, it would stay up for as long as possible. And you wanted to make sure that, you definitely didn't have to do a deployment, because that was just way too stressful, because to do a deployment, you had to talk to your project manager. So you also, tried to avoid doing that. But that didn't mean that nothing changed. And so in order to give you flexibility at runtime without actually stopping the application or doing a deployment, it was all about the late binding. So the idea was you could build your application in a generic way, and then you could swap bits of it out and then swap them back in as you discovered security vulnerabilities and that kind of thing. So it was all really oriented towards being reconfigurable without any need for a restart, which is really clever technology. And so fundamentally, these application frameworks, they were optimized for dynamism, which is clever. But of course, dynamism has a cost. There is a tax for that dynamism. And then you say, well, okay, is it worth paying the cost of dynamism? How do I run my applications now? Now, almost always, we run our applications in containers. And even if you don't run in containers, you've probably sorted out your CI/CD and you have a pipeline, and deploying is safe and you deploy all the time. So now, hopefully, the idea of patching an application that's running rather than just rebuilding it and getting a new, fresh, clean container, should make you go and go, ooh, it doesn't seem like a good idea. And yet we're still paying the cost of that dynamism in our Java applications. So it is completely pointless to have a highly dynamic runtime in a container environment, because you will just rebuild the container. That's how you do it. So With the Java dynamism, what's going on under the hood? Well, normally when you start a Java application, you have a little bit of stuff that happens at build time, and then there's stuff that happens at runtime. And so at build time, you will do your packaging. You'll, sort of make it into an archive with Maven or Gradle. And then almost everything else happens at runtime. So at runtime, you find all of your config files, you find your YAML, and then you wish you hadn't found your YAML. You found your XML, and then you realize that actually YAML was okay. So you have to parse all these properties, and then you have to do some class path scanning, and you discover annotations because there's annotations everywhere. And then you try and load and unload classes just to see what kind of environment you're in, so you know what features you need to enable or disable. And then once you've done all that, then if you're a JVM, you can build this meta model of the world. And then finally, you can actually start doing the things that involve startup, like starting your thread pools, doing your IO, that kind of thing. And then once you've done all that, you're at last ready to do work. And so what happens if you start the application more than once? Well, you don't need to repackage it. It's still a jar. But everything else that you do has to be done every single startup. And so if you're running in a modern environment where you start these things up and down all the time, it's pretty sad because you're redoing so much work every single time. So let's look at like a few examples of what kind of work gets redone and how they affect things. So for example, we see an impact of redoing this work on throughput, because the app, or sorry, this isn't throughput, this is startup speed. So when it tries to start and you have something that's using transactions, so JTA, it will try an auto wire. And so it will do a class 4 name of a likely JTA implementation. Hopefully it finds it. If it doesn't, it goes to the second most popular one. If it doesn't find it, it goes to the third most popular one. And then it keeps going. And then, it tries the really niche ones, and then it tries the super niche ones. And of course, each time, I haven't animated it for each one, but because it would be too annoying, but each time when it doesn't find it, it has to throw a class not found exception. This is really expensive, and it does it 129 times every single time you start. So of course that's going to affect the startup time. And that's just, one little example from how Hibernate starts. And, all of the service bindings go through this kind of process. And of course, it affects the footprint as well. So with another Hibernate example, the JVM, it spends a lot of time loading classes for specific databases. So for example, for an Oracle database, it will load a bunch of classes. If you're not using an Oracle database, then, it works out that they're not used. And so then the JIT will then have to spend more time unloading them. And for example, with Oracle, there's around 500 classes that Hibernate has to load, which are only useful if you're using an Oracle database. And that happens every single start. And I mentioned throughput accidentally at the beginning. And it's worth coming back to that, because the true cost of loading these classes isn't just that it slows down your startup and that you use more footprint. There's other implications. So how the JVM works is if you try and invoke a method, it does what's called method dispatching. So you might have an interface, and then there might be a bunch of possible implementations of that interface, and it has to figure out which one it should actually send the call to. And so it sort of, will try each one and then figure out, okay, nope, it's this one. And this is called a megamorphic call, and it's kind of slow. On the other hand, if you only have one potential implementation of that interface, it can bind it really tightly. And so that's called a monomorphic call, and it's fast. So you can see that there's a real throughput advantage as well to getting rid of all of that sort of exploration of like, maybe I could load this, maybe I could load this. Maybe we have all these classes that we're never going to use because we don't have a backend that matches them. So that's bad. How do you fix it? Well, what the Quarkus team realized that they could do is change around the initialization. So instead of doing all of that initialization at runtime, you could do the bare minimum initialization at runtime and do more of your initialization at build time. And so then it's just, things like thread pools and IO and that kind of thing that has to be done at runtime. And everything else is done as part of the application build. And so what that means is that if you start the application repeatedly, as you're going to do because it's 2024, those repeated starts are efficient, which is cool. And so it means that all of that wasted work that was happening just isn't happening anymore. And then as kind of a nifty side effect of doing it this way, when you move your initialization to build time, it means that native and GraalVM almost works for free as a side effect of what you're doing to make running on the JVM faster. So it's a really nice architecture for this. And so when you do more upfront, it speeds up the application start, as you'd expect. It shrinks the memory footprint because you don't have all these classes that you're not using. It improves throughput, which is maybe less expected. But there is a corollary. So there's always a but, right? For this to work, your libraries have to participate in this. Your libraries have to be doing more at build time, not just at runtime. Otherwise, like some parts of the application will have a fast startup, and then other parts of the application will be doing things the way they always used to do and slowing it down. And so this is the other thing that the Quarkus team did, is they said, we can make things like Hibernate work in this Quarkus-y way, but if we want the whole ecosystem to work in this way, we need an extensible build process. So one of the other secrets of Quarkus, although it's not a secret, because if it was a secret, then we wouldn't get the community involvement that is needed, is to have this extensible build system and to have the right plug points so that the whole ecosystem becomes faster. So in Quarkus, what we do is we have this idea of build steps and build items. And if you want to contribute build steps and build items, you write an extension. And then any extension can make these build steps and build items. And what happens is your extension will declare some build steps, and the build step will consume build items, and it will produce build items. And so then what the Quarkus framework does is on application startup or on build, it will order all of these build items and build steps so that everything gets the inputs it needs. And so the framework automatically determines this correct execution order, and it injects the parameters and that kind of thing. And the build items are the communication mechanism between the build steps. So this sounds kind of complicated. How do you debug this if the framework is automatically ordering things and injecting things? You can in the Quarkus Dev UI if you want to see what's going on, which is particularly useful if you're writing an extension. You can go and you can look at your build metrics and you can see what build steps executed and how long it took. This is mostly useful for extension authors, but it is part of that extensibility that we have. So a natural question at this point is, well, if you move everything to build time, and I am a developer, I spent half my life already waiting for builds. Why would I want to do more at build time? Doesn't that long compilation make things terrible for developers? And I think the answer would be, potentially, if you didn't have live coding, yeah, that would be a worse experience. And so one of the sort of the early things that the Quarkus team did was get a dev mode, which is live reload, live coding. So it means that when you make a change, it's reflected instantaneously and you don't have to wait for that long compile. So this is cool because we went from something that was potentially really bad for developers to something that's way better than the alternatives and everything else that existed for developers in the Java ecosystem. And when you're doing the live coding and the live reload, if it would restart Quarkus every single time, for every change, that would be kind of annoying. So it works out how much it needs to reload. So the smallest level is if you do something like a file reload, for example, like a style sheet, it will just reload that. If you change some code, usually it will be able to use a JVM agent to reload just those classes and get them, those changed classes, and get them onto the class path. But some things that, if they're fundamental to the build process, if they're fundamental to the Quarkus architecture, if you change those, it will have to do a full restart. And so then that's a little bit longer, but you can see, it's not too bad. Here in, the example I screenshotted, it was 1.4 seconds. And so I think there's sort of a nice complementariness here, which is because we start so fast, we can afford to do those big restarts when we need to, because even the big restart is actually starting really fast. And I think this is important as well, because that developer experience is something that the Quarkus team have been thinking about since the beginning. And this is, when you compare it to something like Rust, is a huge difference, because Rust is really efficient for machines and really inefficient for people, potentially. And I think, we shouldn't call people resources, but people are fundamentally the most expensive resource. And, our time is valuable, which is why we sometimes get called resources. And for our organizations will work a lot better if our time is optimized. So really, what all of our technology should be working on is not just making machines efficient, but making people efficient. And I think this is something that, we're in this Quarkus ecosystem, we're in a really good place on. So I tried to think about, like, what frustrates me when I program in some languages, and, what makes things really easy and makes it just go. And I think what's really important is languages should make it hard to get it wrong. So that means having things like strong typing. It means things like having garbage collection, because otherwise it's a nightmare. And we need that tight feedback loop. So if I'm manually testing and if I'm doing automated testing, either way, I need to know really quickly if I've got it wrong, because probably, despite the first point about making it hard to get it wrong, I've got it wrong the first 6 times. So I need that feedback so that I can get it to the point where it's right without having to wait for ages. And of course, being concise is really important too. I don't want a language that's all verbose. I want to do the bare minimum of typing. And so I think in the Java ecosystem, like, that strong typing and that garbage collection are big productivity aids. And, Java's just given them to us. So yay. For that type feedback loop, this is something that we're really getting with Quarkus. And so we talked about how Quarkus gives you that. So what are some other things that Quarkus gives you? Well, how do you get, so what does developer joy look like, and how do you get it? We know it's important. We know it's really important. And one of the things that Quarkus does that enables a better developer experience is it indexes everything, and it makes this really good index, and that index is available to the ecosystem. So for other libraries, they can build an extension and they can see what's in the Quarkus index, and they can use that to save developer time. So again, what a lot of frameworks do on startup is, because everything is done with annotations, they need to find all of the classes and all of the interfaces that have whatever annotation. And then they need to find classes that implement or extend some library. And Java doesn't give us a whole bunch of help with this. The reflection package doesn't give us this. Annotation processing can help to a certain extent, but it's not at the right stage. So what Quarkus did, because we knew we needed this and we knew it was really fundamental, is we wrote a new tool which is called Jandex. And Jandex is basically like offline reflection, because we need that exploration of the class path to happen at build time, not at runtime. So once you have your Jandex index, there's all sorts of cool things that you can do with it. And again, this comes back to challenging assumptions. We've been programming the same way for so long. We just assume that developers have to type this and, developers have to do that. And what if they didn't have to? So here's a little example. It has always really frustrated me that if I want to add logging to a class, I have to write this line, public static final logger log equals logger.getLogger thing.class. Why do I have to type the name of the class? Because it should know what class it's in. I'm not going to try and log for a different class. And it's because code often gets cut and pasted. This is just, extra typing, and it's a source of errors. So what if instead you just didn't have that line, and instead you just call a static method on the log and it works? Well, that's what Quarkus does. And I think, you don't have to do it this way, but I think it's so useful because fundamentally, for productivity, don't make humans tell the computer what the computer already knows. That's just silly. And then the next question is, well, why haven't we done this before? And usually at this point, people may start to get a little bit itchy too. And they say, well, yeah, I tried some framework that did this, and my application was really slow. That's not the case with Quarkus, again, because we're doing this. We're not doing this like at runtime. Normally when you do reflection, it's at runtime, and so it's really expensive. But with Quarkus, because we have that offline index, we can do it all at build time. So you use Jandex to find everywhere that the log class is used, and then everywhere that it's used, you just change that code to have a static field, but the computer makes the static field. And so then you can change all of the calls to that static method with your new field. And you do it all at build time is the key. So you don't pay that runtime cost, which is what a lot of us kind of object to when we see this kind of code. So under the covers, what you end up with is something like this. So we call the logger method rather than what was typed in the code when it's compiled to bytecode. And this is a trivial little example, but there's some quite big productivity gains that we can get using similar techniques. So, for example, with Hibernate, if you're using Hibernate for your DAOs, you usually end up with quite a lot of boilerplate for your query. So you need a query for list all, and you need a query for this and a query for that. And it's just kind of annoying because they're almost the same, but they're not the same, and there's a lot of them. So you probably can't see that, but the point is there's a lot of code. And so with Quarkus, we added a library on top of Hibernate called Panache. And what Panache does is it allows you to get rid of most of that code. And so if you're using a DAO pattern, you have almost no code. And the other thing that Hibernate enables, which I really like, is that you don't have to use a DAO pattern. So instead, you can use an active record pattern. And so then that means that instead of having to have a separate repository class and then all of that, you just have it in one class, which to me feels a lot more natural. And I think if you've never tried to do something like this, you look at it and you go, well, yeah, so you just inherit a superclass and stuff works. Why is this hard? And it has to do with what that superclass would have to do. In Panache, we have a superclass called Panache entity. And if you try and imagine writing this, you could have a method called something like list all, and it could have a generic signature, and that would be fine. But if it's in the superclass, you have to provide the implementation too. And that's where it gets harder, because in the superclass, you don't know what kind of entity this is. But in order to do the hibernate query, you have to know what kind of entity it is. And so then you're stuck and it can't be done. Whereas with Quarkus, because we have this ability to adjust the code at compile time, we can do things like, if I have something that extends Panache entity, it doesn't actually change the Panache entity to be specific to an order, because that would be impossible. Instead, in the original class, we see that extends Panache entity, and then we add in the methods that are generated by the computer, so I don't have to write them at build time. And I think this is really nice, because here what we've got is we've got that machine efficiency unlocking the human efficiency. So there's, again, they're complementary. Of course, there is, some people, again, will be feeling a little bit itchy, and they're kind of going, oh yeah, I tried magic once. I used Lombok. That was a mistake. I don't like it. And yeah, that's fair enough. So Quarkus unlocks this magic. It definitely doesn't make it compulsory. So, I think it's really important when you write these kinds of magic systems that they have to be optional, because, doing less is an efficiency. But you don't want something that's so narrow that if, as soon as you fall off the golden path, you're fighting the magic, because that is not efficient. And I think another thing that's really important with all of this is you can write some beautiful things, like, some of the low code systems. They are beautiful in a demo, but you have to optimize for real use, not just for demos. So there's no point in having magic if it's not actually useful in day-to-day life. And I think what we've tried to do is, get this magic that is actually useful for in production at scale, well beyond the demo. And again, one of the things that, enables this is the fact that our performance is so good. And so then the question is, okay, well, but why is our performance so good? We've got various techniques that we've used, like doing stuff at build time, but, is there a common factor? And so I tried to think about this, and, I was thinking, well, one of the earliest things that we did was that work to move the Hibernate initialization to build time. And this was done by my colleague Sanne Green-Navarro. He was really kind of, developer zero on Quarkus, and he did that Hibernate work to make it possible for Hibernate to boot in advance effectively. And a lot of the recent performance optimizations that we've had have been done by my colleague, Francesco Nigro. And, he's a performance engineer, and he's just done a ton of performance fixes for Quarkus, but also up and down the stack and around the Java ecosystem. And, I said I wasn't going to talk about virtual threads, which was disappointing. I do have one little bit on virtual threads, because my colleague Mario Fusco, he does a lot of work with things like Groovy, but he's also done some work with Quarkus, and it's been really impactful. So with virtual threads, they're another one where I think sometimes there's the gap between, certainly at the moment, there's the gap between the demo and the okay, well, how does it look at scale in production? Because one of the problems that you have with virtual threads is what's called pinning. And what that means is that there's certain operations that a class can do that will devirtualize your virtual thread, and it will lock itself to the carrier thread, and none of the other virtual threads will be able to run, and your application all of a sudden has this horrible bottleneck and grinds to a halt. And there's various things that do pinning, never intentionally, but these libraries, they weren't designed with virtual threads in mind. Virtual threads is new. And one of the big big instances of pinning that we found when we investigated was in Jackson. And of course, Jackson is used in a lot of places. And so Mario Fusco put in a PR to Jackson to make them much more friendly and compatible with virtual threads so that you didn't get this performance hit from virtual threads if you were using Jackson. So that was really cool. So, again, then the sort of the question is, okay, well, what is the common factor here? And one common factor is, apparently it's being Italian. And I should add, of course, there's a ton of really, really brilliant engineers who've worked on Quarkus. Each release, we give out a T-shirt that says "I make Quarkus," whatever version it was. And so for Quarkus 3, we had to give out almost 1,000 T-shirts to all of the people who contributed. And I don't think we've done the statistics, but definitely only some of the people that we gave the T-shirts to were Italian. And I should add as well, because I know there's sort of a big Brazilian population in the Quarkus Club, that some of the people that we gave T-shirts to, including George, were Brazilian. So do you have to be Italian to make Quarkus efficient? No, but I think you do have to have this quality of teimosia, and you have to have that stubbornness, but then you also have to work hard, and it may be that you get this a little bit more if you're Italian. I don't know. But if you think that's true, you can buy the sweatshirt that proves it. But, another really important thing to bear in mind here is, this isn't just a question of, finding something and doing it. This is really, really hard work, these kinds of performance optimizations. And Franz, especially, he's like a dog with a bone. And, you just, the performance, there's so much work of, you profile the application and then you find something you can shave off. And then you profile the application and you find something you can shave off. And you profile the application and you find something you can shave. And you profile and shave and profile and shave and profile and shave. And it is a lot of work. And then the other thing that sometimes happens, of course, is you find a mystery. And so instead of that cycle of profiling and shaving, you need to do something different. And so one of the ways that Franz describes his job, which I really like, is obsession as a service, or OAS, because he really is, if there's a problem, he will not let it go. It is that teimosia again. And I want to talk about one example. We participate, we sort of submit results to a benchmark called Tech Empower. And we were a bit confused because our results on Tech Empower weren't what we expected. And Tech Empower tends to run on machines with a huge number of cores. And what we were seeing is that there was a difference between running on those kinds of systems and running on like a normal number of cores, like 4, 8, or 16. So whereas with Tech Empower, you'd be like 64 cores. So with the small number of cores, we would see a flame graph that looked something like this. But when we went up to a large number of cores, the shape of the flame graph changed. And there was a whole bunch of stuff, where nothing was happening. And the application seemed to be stalled. And we couldn't figure it out, and it wasn't turning up in the traces. None of our normal performance tools were finding this problem. What was going on? So I think probably a lot of people would have gone, confusing. But what Franz did was, with another colleague, Andrew Haley, who is not Italian, he read 20,000 lines of code. He read the JVM code, 20,000 lines of assembler code, in order to figure out what could be going on. And he eventually did find a pattern that seemed to be triggering the problem. And the pattern that he found was an instance of check. And at this point, probably most of us sort of went, that's really bad. because if an instance of check ruins your performance when you have a lot of cores, that affects, well, like everything. So it affected Quarkus core, which is why we found it. It affects Netty hugely. You know, it was in the Netty stack that we were seeing the problem. And then, of course, it affects Hibernate, it affects Vertex, it affects, you know, other things in our stack like Small Rye Mutiny and Small Rye Common, and, you know, Infinispan and Camel and Drools and Optiplanner. And it also, interestingly, affects the Java class library. You know, this is everywhere. And then the next question is, okay, well, are we sure this is a problem? And we were able to confirm it was a problem because we started fixing it and we started changing our code to avoid these instances of checks. And our performance on Tech and Power in the many core case had a huge improvement. So we kind of knew that, you know, we had found a real problem, and the real problem was kind of surprising. So you can see again, this is, you know, just a micro benchmark. So obviously you should be cautious with micro benchmarks, but it showed that, you know, making these code changes had a huge impact. And this was good because we'd found a problem and we'd sped it up, but it was bad because we didn't like the fix. So for example, this is a little bit of our code where this is what we had before, and we did a fix and we got 30% more throughput. But you can see, like if I asked you which code do you like better, you would like the before code better. This code is not nice. And I was looking through this code and I was looking through the GitHub history, and this makes me laugh because this is the kind of PR where the developer puts the PR in and then they basically apologize for the PR as they're doing it, because they're like, well, I'm not really a fan of this code, and it's not idiomatic, and this is going to be really hard to maintain. So again, you know, it's back to this trade-off of human efficiency versus machine efficiency. But, you know, in this case, it was the Quarkus team suffered so that everybody using Quarkus would have a more performant optimum experience. And the other thing that the Quarkus team did is there was a defect raised against OpenJDK for this exact issue, but I don't think anybody had really realized how serious a problem it was because, of course, those kinds of huge multi-core machines have only recently started to become available. And so we kind of explained on the issue that it was a problem, and we then eventually, I think, put in a PR as well. So now the issue is fixed. So hopefully in upcoming JDKs, this won't be a problem, and eventually we'll be able to back out the horrible code. But the other thing about this kind of performance work, so like this was a huge one, right? Where we made a change and we were able to see, you know, order of magnitude improvement, you know, tens of percentage points improvements. But a lot of performance improvements and also a lot of performance regressions, they're not like those big things. They're a lot more like frog boiling instead. And so we run performance tests regularly, as you would expect, and we do statistical analysis to see what's going on and to find regressions. And we had a problem recently where Matt Rabel came and told us that our performance had got worse. And we kind of thought, no, we're running the tests. Our performance hasn't got worse. And if you look at the graph I'm showing you, in that graph I'm showing you, it definitely looks like performance is not getting worse. Performance is getting better. Lower is better. But there was a complexity, because if you look at a bigger time scale, you can see that there was a big regression that then masked something that was actually, and us fixing that big regression masked the fact that other things had got worse. And statistics is hard. Our analysis algorithm hadn't caught that particular case. And in fact, even looking at it by eye, it's pretty hard to see. So again, once we found the problem, we did a bunch of work, and, you know, we were able to undo that creep. But it was something that was a bit of a lesson to us, I think, in terms of making sure that we don't rely too much on one statistics algorithm, and we do try and make sure that we catch that kind of thing. And the problem happened. The problem was in the configuration code, and it particularly happened when you had a lot of configuration variables. And I really, really like the fix, because the fix is coming back again to this idea of challenging assumption. Because the JVM's string comparison algorithm goes from left to right, which is completely logical, because as a human being, as a English speaker, I read left to right, and that's what most languages, not all, but most languages read from left to right, including the US, where probably that code was written. So the thing is, for something like config, the way humans tend to structure their config is they will have prefixes. So they might have like a Quarkus prefix for all the config, and then they might have some other prefix, and then they might have some other prefix. And so the actual point of difference is all the way on the right-hand side of the string. So if you read from left to right, you have to go through all of those characters every single time. If you read from right to left, you find the difference much faster. So, these are the sort of weird little tricks that if you put in enough work, you can figure out that you need to do. So I think for others who are looking at the performance of their own applications, I would definitely say performance is something that you have to invest in. And, you should invest in your own Francesco. And, he doesn't have to be Italian, or she doesn't have to be Italian. That is optional. But they do have to have that determination. And there's one final trade-off I want to talk about, which is sustainability. Because we often think of sustainability as, again, one of those classic trade-offs where, there's doing the things that we want to do and saving the planet. And, so far we've all been very much on the side of doing the stuff that we want to do, and saving the planet has been kind of an afterthought. And this trade-off is a bit depressing, because we all want to do the things that we want to do, but we also kind of want to save the planet. I think there is some hope here. And one of the things that gives hope is something that I've called the room model. And naming is the hardest problem in computer science. So it turned out that the room model was a really bad name, because if you search for room model, and I spelt it with an indeterminate number of R's and O's, the first thing is that Google will say, oh no, you don't mean that spelling. Let me spell it the normal way with one R and two O's. But then, even when Google does that spelling correction, you will find a room model, and it is not my room model. It is a model that was invented by Dr. Room, which I just love, because there was someone called Dr. Room. So naming is the hardest problem in computer science. I should have Googled the name before I named it. Duh. But there's another problem with the room model, which is if you want to find some of the graphs for the room model, or actually even if you're just doing a normal Google search, it will bring up the images. And so if you spell it the normal way, it won't have any images. If you spell it with lots of R's and lots of O's, it will say, I know what you're looking for. But it is not anything to do with sustainability. I had to sort of blank out parts of this because it was barely safe for work, the Google search results. So this was not what was intended. So what's my room model? Well, I started thinking about this when I was looking at the paper that probably a lot of people saw. It kind of went around the internet, of looking at the efficiency of various programming languages. And they had a column for time and they had a column for energy. And the interesting thing is that they normalized the languages and they ordered them. Those two columns, the time and energy columns, are almost exactly the same. And so I graphed it, and you can see that that line is pretty much straight. So energy and speed are correlated. And we can actually see this in Quarkus as well. So we did some benchmarking where we looked at the energy consumption. And here, the line length shows the maximum throughput, so longer lines are better. and the height shows the carbon footprint. So lower is better. And you can see that the things that have the longest line also are lowest. So you go faster if you're more energy efficient, which is kind of awesome, because this is another case where we beat the trade-off. And by using Quarkus, or by using, anything like that, where you have this sort of great developer experience and also this great performance, you get to both save the planet and code the way you want to code. And I really like this because it's the machine efficiency is helping you gain that human efficiency. So to wrap up, the efficient languages and frameworks like Quarkus, ideally, really, you want to be looking at both the machine efficiency and the human efficiency. And the way you get the machine efficiency is you have to challenge the assumptions. You have to only do work once. You have to move work to where it hurts less, like build time, and indexes are your friend for efficiency. And then for the human efficiency, again, it's about challenging the assumptions. And people become efficient if you tighten the feedback loops for them. And don't make people tell the computer what the computer already knows, because that's just annoying. And so with that, I will stop. Again, thank you very much. If you'd like the slides, they are available. And I think that's all. We've got just a little bit of time for questions.
So Holly, was really nice, amazing presentation. I really like the idea of stubbornness as a service, right? And in Portuguese, the word is teimoso. It's quite similar with Italian. You can say teimoso as a person, or teimosia as a action.
Yeah, it was. You probably couldn't tell because I can't pronounce anything, but it was actually the Brazilian Portuguese word that I was trying to put into my slides. Yes, I had George's help.
Nice. Was I will use it for now on stubbornness as a service. I really like it. So thank you so much again, behalf of the Quartz community. Was amazing. Thank you so much for your time and effort.
Yeah, my pleasure. Thank you.
We have a nice number of people watching, but maybe they are shy and they didn't wrote anything. Anyway, if you are watching this, you don't know what's the Quarks Club. It's a Discord channel. Holly's there, so go there, tag her, poke her, ask your questions if you're watching on demand this video. I'm quite sure she's going to be really keen to try to answer everything. And you can get the slides on the QR code, as she said. And that's it for all today. So stay tuned, because we are going to have more guests soon, hopefully. So thank you so much. Thank you, Holly. It was a really nice presentation.
Thanks, everybody. See you.
Bye.